All right, well, we have one side working and we have one mic, but we're going to go ahead and get started anyways. Again, thank you for coming out. My name is Neil Maida. I work with ISS, and this is Alex Wheeler. And Alex and I have done a fair bit of research on antivirus, and we're here talking to you today about the security weaknesses in the models of antivirus and how antivirus could potentially be the weak point that a hacker might use to compromise your network. To give you an outline of the speech today, we'll give you a background on AV. It'll be very quick. Most people here are very familiar with it, how it works. It's a technology that hasn't evolved that much, and so there's not that much that's new to talk about it. We'll go into code coverage, how to audit AV products, how to find the places to audit. Just where to get started is usually a large part of it. And we'll talk about some of the results of the auditing that we've done. We have some new results to announce today, too. And we'll go into that. And then, there's still a ton of research to be done in antivirus. And, there's some future areas that are very interesting that I'm sure we would be interested in exploring, and many people in this audience would be, too. And so we'll talk about those today. Can you take that?
Okay, so we're going to start off with explaining why go after AV. Why is it interesting? And the summary reason is it has a really high ROI. You get a lot of bang for your buck. What we mean by that is these libraries run on pretty much every system available. Gateways, clients, servers, ISPs implement them, if you guys have seen the AOL ads and such. They even try to sell these products as layered technologies. And a lot of companies try and implement like XYZ vendor at the gateway and a different vendor on the client. So again, maybe because you only have McAfee as a client, but you may be vulnerable with Trend Micro at the server. So you have two different targets right there with one piece of security software. And as always, owning security products is really fun because they're supposed to protect you, not hurt you. So whenever you can find bugs in them that open you up to more risk than you already were exposed to, it kind of defeats the purpose of the security product in the first place. So AV, in our opinion, probably has one of the hardest jobs on the security software side. Like firewalls, yeah, it's kind of hard because there's standard streams and you got to protect against a lot, but AV has to process all untrusted input. They can't just like block things because users want functionality out of their systems. So in order to process all this, they have to mimic hundreds of applications, which is a lot of surface area to cover. And then again, it's kind of annoying. People are always like, I run Mac or I run Linux, so I'm not susceptible to viruses. Well, your AV is susceptible then. Because these things are designed to run on lots of different platforms. Some of the advisories we've issued have even run on stuff like AS400 and things like that. Like I would never put antivirus on a system like that, but they're available to run on it.
Just the quick background for those of you who don't know a lot about antivirus. The technology really hasn't changed in terms of detection capability in 15 years. There are a lot of newer features, but if you look at how the majority of these products will catch the majority of the viruses that are out there, it's really a signature or pattern matching approach. And it's very complex. The process in order to get the data stream to match the patterns against is very complex. They have to decompose many different file formats, decompress archives, understand Office file formats and so on, but in the end, it comes down to a pattern match against the data stream. There's a whole science about how to create those patterns. There are papers you can read on it to avoid false positives, false negatives. I don't want to oversimplify it, but at the same time, it really hasn't changed that much in a long time. If you look at enterprise versus consumer AV, what we found during our research is that the same engines run on the $20,000 gateway appliance that run on your $20 desktop piece of software. We created exploit files, tested them against the appliances, put it on a desktop, and saw the exact same code crash in the exact same place. What you're really paying for when it comes to enterprise software versus consumer software is the ability to centrally manage and update, which is key. But under the hood, you're looking at the same piece of software across all platforms for most vendors. And there are some common core components to these things. The I/O filters are key. The antivirus product is only useful if it can get all sorts, scan files that come into your system every way possible, be it over a file share, through the web, off a CD, over IR. They have filters everywhere in your system. And so from an attack standpoint, what that means is that there's no shortage of ways to get untrusted input to an antivirus product. It's not one of those things where you have to sit and think about how you get untrusted input to it. They're designed to deal with untrusted input. And then they deal with so many different file formats. And these formats are usually segmented off and coded in separate engines they're usually done in C++, and they are related or inherited in many cases. There's some standard features. Updates are key. With traditional antivirus, your protection is really only as good as your last update. And if you look at where the majority of the infections occur, it's in the time between a virus appearing and the update. And so keeping them updated is key, both to protect from viruses and to make sure that security issues in your antivirus are not being exploited. Vendors have what we call multi-threat detection, things such as heuristics or behavioral detection. And in most of the traditional AV products, if you look at the success rate of catching things through the newer detection mechanisms versus signature-based, it's relatively low. And so still the core of the detection is based on signatures and pattern matches. There's some common configuration features within these products that have some security consequences. Scan level, for example, is how deep how far recursively will these products scan? Will they scan a zip file within a RAR file, within an ARG file? That's usually a configurable parameter. Scan sizes, usually related to how large a file will they scan. And there is a configurable limit in a lot of these products, at which point if you see a file larger than that, they won't scan it. And scan method. A lot of these products have the ability to turn on or off some of the newer detection mechanisms and to turn on or off things such as disinfection. And so if you're looking at a AV product from an audit standpoint, the default configuration becomes very important because most users will not tweak these options. And so there may be a large amount of code in an AV product that will simply never be reachable in standard configuration.
Okay, so now we're going to actually get into how to start auditing AV. And I think a lot of these concepts or ideas we're pointing out are applicable across a range of software, no matter what you're auditing. We're going to speak specifically to AV, though. So you get this binary, and you want to start finding bugs in it. And a good question is, where do I start? Because you want to use your time wisely. It's not really practical or efficient to start going through the thing start to finish. It's much quicker to start off where you know that users have influence over certain functionality and nail those items first and start investigating those items first. And the best place to start is with things you already know. So standards, a lot of standards have like maximum sizes you can search for, or magic numbers or strings. Like for instance, ARG, they have a maximum header size of A28. So you can just do a search for that, a binary search for like a compare instruction. Is this register bigger than A28 or this value bigger than A28? Well, that's kind of a unique number, and I would suspect that might be an ARG processor right there and then. And in fact, the buffer they're retrieving the values from, you can probably assume that that's direct user input or direct input from the file, which is created by users. Field sizes like PE, OX28, you'll see that 40 bytes all over the place because that's how big a section object is. tar has a 512 bytes size. So whenever you see reads for that request, you can pretty much assume it's a tar file. And we've got some examples here on, real quick, how to search through some examples in IDA, which is the tool I think most of us use. So just a quick binary search, A28. And right here you see two instructions, compare, compare. That's definitely an ARG file, and as we mentioned before, there's other things to look for. Here's the signature for ARG. So every header has to have that signature, and you know right away you have context. And these names right here, they start out like this. So if you're looking at these functions and you're like, okay, they're around these user input values, I can start naming them because this looks a lot like a read from file. Here's all the parameters, the destination, the length. So just start naming them. And you see how we already used that. So you see how this trickles through the program too. Once you name one function that's commonly used, it's money because you can look through all the cross-references to it. So maybe this didn't have a bug here, but we're going to hit it and then check out all these cross-references. And this is all attack surface you can cover pretty easy and pretty much guarantee that you have context right there and then that this is user input. And if you notice, I make notes after I check things, just because a lot of times you'll go over the same piece of code from a couple different directions, and it's really helpful not to go over the same piece of code over and over. So once you check some cross-references, just mark off that it's checked, because these binaries are pretty big and it's easy to get lost.
An approach like this is absolutely key. If you look at some of the sizes of these binaries, they're 10 and 12 megabytes, millions and millions of lines of assembly instructions, and the majority of it is not influenced by user input. And so if you don't have the starting point, you're absolutely lost.
Yeah, that's a frustrating thing, actually, because if you don't have a starting point and you start just looking for bad code, you're going to find tons of bugs, and 99% of those bugs are going to be with the initialization files or update files, things that the user has no control over. It's just solely the vendor's code, and it's some internal management scheme. So another great place to start, probably the first place I always start, and I think Neil can say the same, is directly where the user input is. So in networking, you want to read or receive from, and in AV, these are all file-based user input, so read. And read is really easy to spot. It's usually not named. It might be wrapped in a couple different layers for different file formats, and you can tell just by the parameters. So if I see a length parameter being passed in a destination, and then watch what they do with the buffer after that read, if they're checking bytes and signatures, that's an easy read to spot right there. Some interesting things to observe about these read wrappers is they truncate length. So you can get a 16-bit overflow without doing a negative mem copy, which if anyone out here has tried to exploit negative mem copies, they're kind of difficult because usually they access violate on writes instead of anything else.
Another very interesting place to look is anywhere the antivirus engine will deal with memory allocation. Any place where there are calculations related to length to allocate is going to be interesting, especially if they combine multiple fields together, try and allocate a buffer for them all in one allocation, and then copy those individual fields into that buffer. At that point, you have the ability to exceed the maximum integer size for your processor and cause a very small allocation. There's some allocators that check for 0 specifically. That has to do with the fact that in some cases you'd be able to just wrap to 0, not above 0. And a 0 allocation will succeed on most Malcolm implementations. And so, in fact, everyone I've looked at will give you a minimum size buffer if you try and allocate 0. And so some of the vendors are more security aware. They have checks for that. Some of them will add an internal header size to every single allocation that they do. And that is it's a very dangerous practice, because then you're open to integer overflows on every single allocation that your program makes. And I don't think we've seen vendors check for those integer overflows when they do those additions for the internal headers that they add. And so from an audit standpoint, as soon as you see that, you begin to go ahead and check all the allocations, and that's just a gold mine right there. And so for any of the people who work for AV companies in the audience, check for that. In fact, could we get a show of hands? Who here works for an AV company? Anyone willing to admit it? One guy right there. No one else?
What's up?
There they are. Okay. Yeah. So there are a few people here who work for AV companies, I'm sure. To be honest with you about the code quality of AV products versus other sectors that we've audited, a little bit of a plug for you guys here in the audience. We look at a lot of code, and we do it for a living. And the AV products out there are much more secure than other classes of software. I think the developers tend to be more security aware. It's just the complexity of the things that they do make it dangerous. Another interesting place to look, if you're dealing with a file that is text-based, would be conversions from strings to numbers. Some people will assume that simply because a file format is text-based, they're not open to integer overflows. You're dealing with text. However, we've seen this many times before where a programmer will simply take a text-based integer, convert it to an integer that's stored in a variable, and then add to it when they're allocating. And then your text-based format is just as open to integer overflows as any other data stream-based format. Byte ordering would be another way you could get context that's a little bit farther outside of where data is directly read from the file. Your processor has a native byte order that it expects data to be in. The file format might not necessarily agree with that. And so if you're dealing with a big endian file format on a little endian processor such as Intel, you have to do that conversion before you can use the integer internally. And so that gives you a fairly good place to start when you're dealing with input. Usually the first thing they do would be to convert it to the correct byte order and then use the variables. Checksum and CRC code, another good place to look. It's fairly easy to spot checksum or CRC code or even crypto code in assembly, because you'll see instructions used that are usually never used by the compiler. Things like rotate right, or you'll see things such as XOR, where the source and the destination operand are different. Things like that, which jump out at you after you stare at this for long enough, and you begin to realize that this is CRC code. And in some cases, it's very, very recognizable. But that gives you the ability to find where your data is being validated or looked at, which may not be immediately after it's read from the file. Some of these products will read data from a file, buffer it, and then come back to it later. And so that gives you that point there.
Okay, so a lot of these file format engines are... Can you guys hear me all right? No? Could someone turn up my mic?
Move the higher up.
So a lot of these file format engines are structured in a way in C++ so that they can be reused and wrapped in other file format engines. It's common to see MZ as the overall external wrapper. We reviewed several antivirus products, probably 7 or 8, and almost all of them have this structure, whereas they'll have a file format engine processor for MZ, which will be used by the PE file format engine, which will be used by whatever file format engine is in it. So with the semantic vulnerability, there were 3 different file wrappers around the vulnerability, which makes it kind of tough to spot. But if you're aware of it, it can actually be useful, because what you can do is you can start building out a notepad of all the offsets within these classes and what they're used for. And whenever you see like an indirect call for like call EAX plus 18, at 18, that's the file format processor for PE. And PE has file format processors for UPX or ASPAC or whatever else. So we just finished talking about code coverage. How do you start auditing to find bugs efficiently? Next we're going to talk about the inefficiencies in AV. Not necessarily memory corruption, but evading the tool itself. So passing viruses through it, which is kind of a moot point, which we'll get to eventually in a couple slides. But basically, anytime these AV engines implement a product like RAR or ZIP, they have to do it exactly like RAR or ZIP. And any differences between the actual product and the AV engine can be exploitable, especially when the engine is stricter than the actual product itself. And I forgot the name of the person who discovered these vulnerabilities originally, but there was a lot of work done on zip archives where you can have like 0-length fields, and the actual zip decompressor will decompress it, but these AV engines will say, oh, that's an invalid size, so we're not going to process this file anymore. Default scan levels are also really interesting, especially when you have self-extracting executables. So no one's going to go in and unzip a RAR and then unRAR a zip and like all these layers, because it's a pain. But if these have self-extracting modules, you can encode this in a couple different layers, and one click by the user, and they're owned. But the AV engine wouldn't scan it because the virus sits 2 layers below where the default scan level is.
A lot of these configuration options are in there because most users will not sacrifice performance for security. And so if the antivirus product is dragging down their system, they'll simply turn it off, uninstall it, reinstall their operating system, whatever it may be. File size limitations, it's very easy to create a very small compressed file that decompresses to a very large file. And so some of the limits, scan limits for these products is tuned relatively low. I think we saw an AV product that had a default scan level or default scan size of 20 megabytes, which is really not that big. I get emails that are that big, once every month. And at that point, you can compress a 400 meg file into a couple K and have it not scanned by AV. Format collisions, this was actually the most interesting evasion we found for antivirus. I'm going to give Alex complete credit for it. I didn't think it would work, but believe it or not, it does. Essentially what this is it's creating a file that conforms to two different file formats. So you could have a file that is an executable, but is also a zip file. I think what we used, it was an executable that was also a LHA file, for example. And these antivirus engines will prioritize which file types they scan in a lot of cases, and they will scan whatever comes up as scan for viruses that conform to a certain file type based on priority. And so if you want to make an archive and you don't want to have it scanned by antivirus, make it look like an executable as well. And these AV engines no longer trust things such as file extensions. All this file recognition is done via heuristics, and so it is, in many cases, it is possible to create these conflicting or these file formats that do collide. And we'll talk about how this was useful in one of the vulnerabilities later. And so we talked about evading these products, and really, in the end, it's really kind of useless to even talk about this stuff, because if someone were a malware author and they wanted to evade your antivirus, all they really have to do is write a new virus. The zero-day protection capabilities from most of these products is really minimal. There's always that window of vulnerability. AV vendors collect malware samples from their infected customers. The business model really amazes me, but it has worked for a long time. And so we see things like the product may protect other processes, but for example, with McAfee and CSA, we saw that CSA was not protecting the McAfee process itself. We see things like that where these products are really ill-equipped to deal with zero-day attacks.
So I just want to make that clear. Every process on the system running McAfee was protected by CSA, memory protection mechanism, except for the McAfee itself. So now we're going to get into memory corruption, which is far more interesting than evasion. The first thing is inconsistent checks. These are pretty much the crux of the bugs that have been discovered in AV so far. Integer issues with inconsistent checks, or just plain out just bad checks. Types like treating something as signed when it should be unsigned. Truncating allocation sizes to 16 bits instead of leaving it at 32 bits. Having an allocation size that's different than what's actually copied can be dangerous. And you'll see a lot of examples of that. And then negative offsets for reading into files. So these read wrappers can read backwards as well as forwards. So you provide a negative offset, they've allocated like 100 bytes because the file is 100 bytes long. And every time they read, they copy into this buffer that they've allocated 100 bytes. Well, if you can make that AV engine seek backwards and keep reading, you can copy in more data than 100 bytes. And this was actually the exact reason that Symantec was vulnerable with UPX decompression.
Another thing that we've seen, we talked about this a little bit earlier, wrappers on allocations. If they modify the length, if they add to it, you have the potential for an integer overflow that leads to a small allocation there. One of the AV products we looked at, I don't think we'll name it, but they had an allocator that truncated the allocation to a 16-bit size. So the maximum allocation you can make is 64K. And I don't even know how that worked. I don't know how the software functioned doing that. But you see these type of errors that are a major source of remotely exploitable vulnerabilities in these products. Another thing is if you have 32-bit fields and you're running on a 32-bit processor, the fields coming out of the file are extremely close to the maximum or minimum boundaries for an integer, whatever that type may be, on your processor. And so 32-bit sizes and 32-bit processors lead to many more integer overflows. And honestly, virtually every file format that you see that's binary on your 32-bit system is going to be have 32-bit integers in it. String-based formats, we didn't find a lot of simple string-based bugs. I think Alex found one. But the majority of these products will parse text-based formats with a well-proven parsing mechanism. They're not going to roll their own. And so they were relatively immune to this type of stuff, but you never know, and it could always be there. More subtle vulnerabilities, such as off-by-ones related to text parsing, may still linger in these products today. But the binary-based formats are really where the majority of the issues were, and they honestly are a lot harder to get completely right.
And the plus is they're easier to reverse than text-based formats generally, in our opinion. So everyone looks kind of tired, and I think this is the fun part of the speech, well, the second most fun part of the speech, where we give you examples and you guys have to point out the bugs. So at first we were kind of like, I don't know if this will be too easy for everyone because it's kind of hard to hide a bug in one slide. So let's see how good that goes. This is we're going to start off easy and get more subtle as we go along. So just raise your hand and we'll call on you when you see the bug.
If no one answers for putting the AV guys on the spot, we know where you are now.
So does anyone see the mistake here? I'll give you a hint. The destination buffer can be overflowed in the read file.
ESI points to untrusted input.
Does anyone know what LEA stands for? What instruction that is? All right, you. Correct. He said there's an integer overflow in the second line. And basically what they're doing is they're grabbing an integer from the file and then adding something to it. And it really doesn't matter what it is as long as it's not 0, because you could set it -1 as that integer from the file. So EBX is -1. Add EDX to it, and it becomes too big. Or it becomes not too big. You guys see where that is? It's pretty simple. The examples are going to get a little more subtle as we move on. So -1 plus 1 equals 0. So ECX is 0. Is 0 above 2000? No. So they use the -1, the length field. EBX still stays -1 as the read length. And the funny thing about AV bugs is this thing is going to error out when the file ends. So you're not going to have a negative mem copy situation in this scenario, which is, again, really good from an attacker's perspective.
Error number 2. Very common error. We've seen it in a lot of products, not just AV.
In fact, we'll be talking about one product today that has this exact error in it.
Same guy? Anyone else know it? Okay, go ahead. Go ahead.
I think the first instruction moves that word is ECX with sign extension, so it's negative.
Correct?
That's half of it.
That's half. So does anyone know the difference between JG and JA? I see a guy raising his hand right back there.
Well, actually, the sign extension converts it into a 32-bit integer with an ECX. Yes?
The difference is if it's a sign computer or unsigned computer.
You're exactly right.
Word.
Yeah. And so basically, there's a less than 0 case here that is not checked for, and so anything less than 0 will bypass the length check and will be treated as an unsigned integer in that memory copy, and so it leads to a huge memory copy based on a negative length.
On the stack. which negative mem copies on the stack are a lot more exploitable than negative mem copies on the heap.
Okay, so far we're 2 for 2. Keep going.
All right. This one actually, Neil found a bug, not in an AV product, but in a certain product. We won't mention it, but I think this bug is really interesting. It's basically a loop doing a string length. And can anyone tell, like, oh, what's wrong with this string length loop? What was that? I can't hear.
Speak up, sorry, I can't hear you. It could overflow? These all can overflow. How? Character overflow.
How? What's the mistake?
I think you're right, but IncBL, yeah. So I think he's got it. I think
All right. So what we're reading into your answer is that because BL can only hold 256 values, if you supply a string longer than 256 bytes, it will truncate and wrap. So once it hits 256, it's going to wrap down to 0. And that test on comparing BL to 100 is going to fail.
Basically, this is a problem you can run into where you're using an integer to store a length, and that integer is smaller than the address space for your processor. And so you know, then strlens can overflow. Any sort of loop that iterates through data can then overflow.
I think these truncation issues are really interesting, and probably there's a lot more out there. I don't think you're going to find a small loop like this in many popular products, but it'll be more distributed throughout more code. The stir copy? Yeah, we deleted the stir copy just because it wasn't readable with all the text on there, but it's a good point. Word.
Yeah, you're right.
So stir copy.
Follow that by like I see exactly what you're saying. Yeah.
Or it could even be a read a byte and stop reading when the byte is 0. Same thing as stir copy. So there's a couple different scenarios where this could be exploitable, and there's a couple different where it couldn't be. But in essence, it's bad code regardless. Okay, this one is what Neil mentioned earlier, an internal allocator that adds, you know, a specific amount of bytes to the requested allocation size in order to account for like internal headers or some sort of administration buffers. So again, we got the LEA. Right there.
The PSI is negative 18 or less.
Right.
Yeah.
That's exactly it. It'll allocate a really small buffer and copy into a really large amount.
There are some AV products that do this for every single allocation in their entire product suite.
Those are really good bugs to find. Okay, so here's the last one. I think this one is really subtle and probably in a lot more products than just AV. What's the first mistake here? I heard someone shout out they don't check the return value. Right, so what could the return value be? It could be an error, FFFFF, -1. And then add -1 to 1, it becomes 0. They allocate a really small amount and do the copy based on the error code. And actually, this bug is in a couple different AV products. Okay, so now we covered some examples, how to start, and now we're going to go over our overall methodology. And we think this methodology is not only beneficial to auditing AV, but also pretty much any product where you're required to do some reverse engineering. The first thing that's great to do, as you saw earlier, when I named get bytes from file, get bytes, you want to identify all the utility functions because it makes your context as a user or as an attacker a lot more clear when you're reviewing code in the binary. These wrappers can be wrappers for file I/O, allocations, and various other things that are pretty interesting. After Neil finishes checking his BlackBerry.
Sorry. I got totally busted on that one. So once you've identified those utility functions, you then want to trace the untrusted input from that point on. You consider that the entry point into the application for the input. And then you probably want to follow it as far as you can and try and pick it up later if you lose it. And so what we do is we'll track these offsets into these huge classes, write them down, and then try and pick them up later in the binary. And so if it's at a low offset into the class, you're probably not going to have a lot of luck because there'll be a lot of instructions that access 4, 8, 10, 16 bytes into structures. But if it's something unique, something a little bit bigger, there's a very good chance that you could pick it up later on in the application. But you want to look for allocations, look for memory copies, anything dealing with the data that causes memory to be written to in a variable way. And at that point, you then have a great way to find the vast majority of the bugs in these products. And the file format processors, reverse the hell out of them. They are, this is where we found all these bugs basically. And the more you understand about them, the more you will find. I know that I've looked at code, thought it was secure, come back, read it a little bit more, and seen something. And so it really comes down to understanding the file format processors and understanding something about them that the developers didn't think about. You're really trying to outthink the person who wrote the code or find oversights that they may have made. And especially in these AV products where these products have probably been audited by either internally or by a third party, you're really looking at code that is relatively secure. You really do have to have an understanding of the code. Normally you just cannot grab for sprintf or store copy and expect to come back with results on these type of things.
Okay, so now we're going to go over some of our results during our AV audit, and I think that these results kind of speak for themselves. The software is supposed to secure you, and it's not. It's actually opening you up to more vulnerabilities, and that's really why we went after it, because it's the most interesting way to find bugs is when you can exploit something that's supposed to protect you. So Symantec, as we mentioned before, it was a negative offset when they're rebuilding the PE header after they've unpacked it. Heap overflow with no character restrictions. It's also pretty money. This one was stable across different service packs and versions of OSs just because of the way the library was implemented. So we wrote an exploit for this on Symantec's secure gateway, the big box they sell for, I don't know, thousands of dollars. And that same exploit triggered the bug on Norton Antivirus 2005 on Windows or Linux, whatever it's running on. So again, we're going to repeat high ROI, and these things are pretty portable across different platforms.
McAfee, this is actually a fairly simple bug, one that I wouldn't expect to see in a commercial security product. It was a stack-based overflow sprintf %s. The classic bug that has been eliminated from most software about 5 years ago. It looked very simple to start, and then we went to trigger it, and what we realized is that it really wasn't. It was in the processing of LHA archive files. Has anyone here ever heard of LHA archives? A couple people. Yeah, it's a fairly obscure old archive format. There was actually an overflow in the Linux client for LHA archives, and they had created a signature for that in their AV product. So they were detecting files that would have triggered this overflow on Linux. I'm not sure what happened when they took the test file and ran it through their product. Maybe it crashed their product. And so they implemented it as a scripted check. It's pseudocode, and it was not the compile code which had the overflow that was flagging this. So you create a file that's about to overflow by one byte, and you get an antivirus message pop up. You roll it back a byte, and nothing happens, and you don't trigger the overflow. And so it was fairly frustrating to see the overflow there in the code, very simple, but not be able to reach it. And so this is where the file format collision evasion came in. Obviously, the scripted engine is going to be less is going to perform a lot slower than the compiled engine, and so the scripted engine was doing prioritization of file types and trying to determine what the file is before it actually scanned it. And so they would run a heuristic over the file, determine that it's a certain file type, then scan it for only vulnerabilities related to that file or viruses related to that file type. And so in this case, Alex created an executable file that was also an LHA file. Executable files were obviously much more high priority than LHA files. The scripted engine would only scan it for executable viruses, flag it as OK, pass it off to the compiled engine, which is a little bit faster, scan for everything. At that point, it would get scanned as a PE file as well as an LHA file. And at that point, you could trigger the overflow. Once you could get to that point, the overflow was very simple and easy to exploit, but there was a very challenging process to get to that point.
Word. Also, I think it's interesting to note that this issuing a DAT file or a signature for a vulnerability in their own product is probably not the best solution. Unfortunately, we've seen this happen with bugs we've reported to these vendors. So the Symantec bug, they're still using the vulnerable file format engine in older versions of the product. And they fixed it by issuing a DAT trying to detect for the possible overflow. So again, if you can figure out a file format collision that works to reach that buggy code, they're still vulnerable. And I didn't mean to pick on Symantec because a lot of other AV vendors have done the same thing. Maybe not with us, but with different bugs in their product that they might have found on their own. We've noticed this is a fairly common practice among AV vendors. And I think it's flawed because, I mean, to issue a signature for a bug in your product assumes that your product is flawless. So if your product's flawless, the detection engine's flawless, yeah, maybe it will work out with the signature-based protection, but I don't think that's the case, and I think even these AV companies will admit that's not the case. So this bug is kind of cool for a couple of reasons. One, pretty much all of Asia runs Trend Micro. All Hotmail is protected by Trend Micro. This stuff is sitting at the Hotmail gateway. It's like 200 million users. 200 million users accounts with one email, which is cool. This bug is the same bug as the F-Secure bug. It was cool to find it because you're getting a 2-for-1. So talk about high ROI. And the extra cool thing about this is it was in the kernel. And this was the first Windows kernel overflow Neil or I did. And we actually got a shell working back on it, which we're going to demo for you for a couple of reasons. One, because it's a kernel overflow on the heap, which is cool. And two, we want to show you how these products are exposed to untrusted input. You're going to see the overflow happen before it even prompts you to copy the file onto the system. And we set up a little virtual machine to, it's bugging me right now, to demo this. And we can come back to it because I don't want to waste time. Oh, we're good. So I think I set the port for this exploit to my birthday, in case anyone wants to get me a birthday present.
Fairly small up there. You should be able to see it.
Okay, what you're going to see is just the shell drop down. So what I'm going to do is just drag this file from my host operating system to the virtual machine. The same thing as emailing the file, which is probably the best attack vector for these AV things. So we'll just drag it over onto the system. Okay. We got the shell back right there. That's a kernel shell. We hijacked the, what process did we hijack? LSASS?
I think so.
I think it was LSASS. Because it's way easier to write shellcode for user land mode. So just because you're in kernel land, it's cool and everything, but it's way easier to execute arbitrary instructions at system level in user land. One of the things you'll notice is it's just now prompting us, do you want to copy or move this here? So we delivered the exploit before this thing ever hit the file system. And that's because these AV engines hook into all the ways users can get input over the network, creating files. Like as soon as you hit save on a file, this would be an exploit. So one of the cool things about kernel exploits is you don't really get a shellback until you specify your drive. So we have to hit C, and now we have the shell. And I think this exploit's pretty robust because, you know, we overflowed the kernel heap, fixed it up, and we can actually exit out of our shell 99% of the time, and the system stays up. So we've exited out of that shell, successfully exploited a remote kernel overflow, and the system's still running fine.
It is fairly challenging to do something like that simply because there are so many different drivers using the same shared pool, and so fixing the heap is very important for these issues.
Oh yeah, I'm supposed to cover this one. Okay, so this was a vulnerability in CA's antivirus engine, and these antivirus engines, just because CA has it in their products, it's also in a lot of other products. So like Zone Labs, I think, was one of the people that were using it, which is owned by Checkpoint. And there was a couple others that are escaping me right now. But again, high ROI. And this was an integer wrap, specifically on the very edge of the 32-bit boundary. So you pass in -1, it added 1 to it, allocated a really small buffer, and then read that much from the file, like the -1 from the file. Fairly easy to exploit. The only trick with this is it was actually dealing with uncompressed data. So you, in order to deliver the exploit and trigger the bug, you had to write up the vulnerable header format and then compress it so that it would be decompressed and then read. So these things are sitting within layers, and it can be kind of tricky figuring out like what exactly you need to trigger the bug.
One thing to note about all these issues, we have worked with all the vendors. There are fixes available for them already, in some cases for several months. And so if you're worried that you have to run out of here and go patch your antivirus, you're probably okay. F-Secure, the vulnerability was in parsing of ARCH files. It actually was the same field as the Trend Micro vulnerability, different code base. They'd implemented the standard in a fairly similar way, and they had made the same oversight. And so it's a heap overflow. This time it was in user mode. So, you know, exploitation of that is fairly well documented, fairly easy. F-Secure, actually, I want to give them a little bit of credit. They were extremely fast at fixing this, and they were extremely great to work with.
By far the most pleasant vendor that we've dealt with so far. One of the things I just remembered about this is I remember reading the spec for ARGE, and the spec almost introduces this vulnerability. I think it said something like, this field will be null terminated. And all the programmers assumed it would be null terminated. Okay, so this is a bug I found recently that I've been working with Sophos on fixing. And again, as Neil said, you don't have to run out of here and patch your systems. AV has a really cool support structure. I think a lot of companies like Cisco or different vendors out there need to look at the AV industry on how to stay current on patches, because a lot of the Sophos, 90% of the Sophos implementations right now are already fixed, and this vulnerability hasn't been disclosed to the public. So this is technically ODE, but most of the people out there are already fixed, which is a really cool feature to have as far as security goes. We'll actually give you a little preview of the advisory I'll be putting out next week, hopefully. Okay, so this slide is, I put it in here because it's kind of cool in the way that, you know, these bugs aren't always just in one function. And it kind of goes to what Neil said earlier. You really have to spend a lot of time writing down offsets and class fields in Notepad and keeping track of all these things, because the bug is actually littered throughout the whole binary. So you need to understand that, you know, point A is where it's initialized, point B is where it's allocated, and point X is where the actual like faulty code error happens. And I'll show you a little quickly where it is. I I don't know if you guys have seen my past advisories since I like to do kind of fun stuff, and I like the Bug's Life. So that's the character from A Bug's Life, and there's the bug. Real simple, as we pointed out. I think this was the second example on our code base. Is this is a 32-bit integer, and they're doing a maximum check against it. Well, they're doing a sign check. So if I pass in -1, that's going to be less than 1,000, and it's going to try to copy in not -1, but the 16-bit value of that -1. So basically, all you have to do to bypass that faulty check is, set the top bit to negative, and then have like a positive 16-bit portion.
One of the questions we've always been asked before when we've given the speech is, well, what about open source AV? And some people ask, well, is it more or less secure? And is it more or less, is it better than, or worse than commercial AV? And I know some people in this room probably have some pretty strong opinions on open source versus commercial software. But up until now, we really didn't know, and so we decided to take a look. As far as I know, ClamAV is the predominant open source AV vendor. In terms of deployment, it's probably not up there when you compare it to McAfee or Symantec or anything like that. However, it is open source and it is fairly easy to audit, so we decided to spend a couple hours and take a look. What we did find is we found quite a few issues in ClamAV, mostly related to integer usage. The majority of the issues were very standard integer overflows. You gonna bring up the source code there? While he's doing that, in terms of a comparison between commercial and open source AV, we found that the open source AV tends to be less mature. It hasn't been around as long, hasn't had the growing pains that commercial AV has had, and so the security code, in my opinion, my qualitative assessment, I think we both agree on this, is that it's not quite as good. But they are getting there. They are fixing these issues, and these guys are volunteers that work very hard on this project, so I respect them for that, for sure. But if you look at this code snippet here, for example, they're allocating length +1, and then reading length, and that's just classic. It's it's the perfect code snippet because it's 2 lines, and the bug is right there. You can almost grep for that.
Same thing.
Is this? Yeah, this is exactly the same issue if you scroll over, I think. Yeah, len +1, and then read len. This next one here, this third one here, this is the FSG issue that we saw. This is actually a reasonably complex integer overflow in which you can bypass both sides of that length check by having 2 slightly negative integers. And so they're checking that you're not before the beginning of the buffer and you're not past the end of the buffer, but they're checking it with 2 different integers, and so the check is faulty. That then leads to what would essentially be a negative memcopy situation on the heap, I believe. I don't remember.
Yep.
And so we found a fair number of issues like this. It's fixed in their source tree now. If you use ClamAV, update. Oh yeah, this is another bug. The reason I wanted to bring this one up is that ClamAV doesn't agree with us that this is the bug. And I'll show you how we found it. We searched for stir copy. Which one is it?
Right up there.
Okay. And it's one of those things where you search for a stir copy, you find something, and then you realize that there is a check somewhere else in the product that is actually associated with it. I mean, it looks almost too easy here. It's just a stir copy file name to a static data buffer. It'll take you 2 seconds to find with grep. You then realize a little bit later that there is a check for that somewhere else in the program, and then you dig deeper as an auditor and you say, well, how can I get around that check? And what we found is that
what Neil found.
We found that that it's possible to have a static data structure be loaded with data from the previous file that was scanned and then used for the next file. So you can initialize it with one file and then have the next file come around and use that data because they don't properly zero out the structure before that. And so it's possible to bypass the length check with that uninitialized data usage and then trigger this overflow. It's really a one-line fix. Change the stir copy to a stir end copy. But I don't think that they want to fix this issue. They don't agree that's a bug. So If anyone here knows the guys and wants to ask them to, I would really appreciate that.
Yeah, it's kind of annoying to point out bugs in source code to developers and have them say no. I mean, it's right there. You know how to program, so it should be fairly simple to address instead of arguing, this isn't a bug, we're not fixing it. Why not just play it safe and say, okay? Especially when these guys provided you with like 4 or 5 other bugs that are obviously remotely exploitable.
Right next bullet.
Do we have anything else here?
Yes.
Oh yeah, future points of interest. You want to take that?
Sure. So obviously there's a lot of work to be done in AV still. And some of the areas that will keep coming up is, these products 4 or 5 years ago didn't have any image parsing, and now they do because of all the bugs that came out in image file formats. So again, in new attack areas, newly implemented code, let's look at it. Again, formats implemented due to wide use, like new file formats, new operating systems, different things like that. These AV products always build in stuff ahead of time to support it, to attract customers.
Their job really is very challenging. I know I've talked to a friend who works for a big AV company, and he's saying that every time some kid who tries to write a virus decides to add a new executable package to that virus, now the AV company has to write a decompressor for that for them, and they're doing that all the time, and it's very challenging to keep up with that. And there is a fair amount of change in their code base, so it is relatively high risk code base. Product administration was another thing.
Oh yeah.
Product administration, the security of their product administration tools tends to be a lot worse than the security of the actual core antivirus library. And so it's kind of scary when you consider that these tools are designed to push updates out across entire enterprises. I mean, with the click of a button, you can send an executable to every antivirus on servers and desktops in your entire enterprise. However, the product administration tool itself is vulnerable. And so they have credentials for all your systems. They have the ability to push updates to all your systems. If an attacker were to find a vulnerability in a product administration tool, they could potentially own an entire enterprise with one exploit. And at ISS, we found an issue like that last year. It's since been fixed, but it is fairly scary stuff. Questions? Yes?
I'm just curious, what antivirus product you have installed on your home computer right now?
I really don't. I don't have one, to be completely honest with you.
Neither do I.
Not that I'm scared to run any of them. They're all pretty good, but I don't use one myself.
But I've installed them all. I think we both have, and I think the major ones out there are pretty good.
They're all pretty comparable in terms of feature set and security. There wasn't one that stood out as the most insecure or the most secure. They all had issues in isolated areas.
Most of these issues are buffer overflow or return flow kind of. So how does they are executed on the data segment or code segment, and how does the execute disable or NX kind of?
The NX stuff, the hardware enforced stuff helps. But if it's a stack-based overflow, there's many attacks. I think one of our researchers is talking tomorrow about bypassing NX stuff. But things such as return into libc stuff still works, depending on how your applications are compiled. A lot of the system services on Windows, for example, have StackGuard-like protection features built into them when they're compiled. We don't see that in a lot of commercial products, and so things like return into libc stuff on Stack Overflows it's extremely easy to do still, even with NX stuff. You don't have to execute code in a writable segment anywhere.
Back there.
You've been quite happy to attack the antivirus companies without mentioning the IC2 parsing bug in ISS's own product, which was exploited by the WikiWorks. Perhaps you'd like to
Sure.
talk about that.
That's a
Good question.
Good question. That's a very fair question. We audit products that our customers run. We also audit our own products. And so after that, my team sat down. We went line by line through all the code in our protocol analysis module. And no one's immune to this stuff, to be honest with you. No piece of software is completely secure. And anyone who claims to be is lying to you. And so we have this great research capability at ISS. And that was a big wake-up call. We turned it around and focused it on our own products as well. And so if any of you out here are ISS customers, you can feel a lot better about the security of our products today versus a year ago or 2 years ago.
As an independent person, I can confirm that.
Can you speak perhaps to the widespread or not widespread nature of the format collisions? I mean, qualitatively, perhaps, have you noticed them a lot?
I guess the attack is relatively new. I don't know. How many products have we looked at for them?
7.
The question is, how widespread are these format collision attacks? What are the potential impact of that? I think that they really come in when you try to do any sort of heuristic detection of file formats. And so it might not be just limited to antivirus. It could be, there's so many different other products that do similar things.
Intrusion detection, IPS,
Absolutely.
same bugs.
Yeah, when we found this issue, we said, well, what are the implications for our own products too? And we found some. To be honest with you, we try to recognize protocols across the wire based on data. And so we did some re-architecture with our own products to make ourselves more resistant to these type of format collision attacks. Yes?
What will be the future of AV?
Yeah, good question. I think that AV, I'll give you my opinion. I'm sure Alex's opinion too. But I think that AV is, it's a key security mechanism. You need it on your networks. We're talking about all these problems with it, but I think you have to have it. Can't do without it. But the major problem I see with AV is that window of vulnerability between a virus appearing and a signature being created for it. The reactive nature, the fact that you have to know about the threat to protect against it in most cases. And so there's some very cool behavioral-based systems out there that recognize viruses based on how they behave in a virtual machine or in an isolated environment, and then determine whether or not they're malicious. And these, I wouldn't say that they're necessarily a replacement for traditional AV, but they are a good addition to your traditional AV mechanisms, and they close that window of vulnerability. They really reduce, they close it to zero. And there are some systems out there today that have very good detection rates behaviorally. Yes?
ISS, what scan engine do you use in your own products?
I don't know. I think it's changed over the last year. I'm not sure. I'll have to check on that.
Have you guys done any testing with alternate data streams and how well the AV products test for that?
I haven't, honestly.
I don't know.
I think the surface has just been scratched with regard to AV right now. Like, we really haven't looked into administration features. We really haven't done thorough audits of any of the AV products out there.
It sounds like most of these vulnerabilities are based on the common use or the common architecture of the way they're scanning, and that they have layers of scanning and interdependencies of even functions. Do you have any idea of how, if you could change that architecture in order to eliminate that type of vulnerability?
Yeah.
How you would do it?
Yes, I think both of us have seen some of the specific AV vendors implement some great functionality as a general API in their products. Like we mentioned, checking for zero on malloc. That should be done in every malloc call. There's no reason to allocate 0 bytes. And also, we've seen some vendors are a lot more thorough with checking for integer issues than others. And I think that, I know Neil Maida and Mark Dowd gave a speech in Halvar Flake 2 or 3 years ago on integer problems at Black Hat. And it doesn't seem like the development community has really caught on to it. The string-based vulnerabilities are being addressed. It's fairly easy to see, like a stir copy or sprintf bug. But integer issues are a little more complex because there's some subtleties that are kind of hard to think of at the time when you're looking at it or programming.
It was interesting when we looked at a lot of these antivirus products. They all had similar architectures, and I'm pretty sure they didn't copy each other. And so I think it may be that there's an efficient way to do the tasks that they're doing, and so they're architected in the same way. But what you'll find, I think, is that when you have disparate development teams writing different portions of your product, you'll see oversights in the way those components interface. And there are a lot of, I'm sure there are a lot of subtle vulnerabilities related to that type of interrelation between the components that we may never find. I don't know. Any other questions?
I want to thank you guys for coming
Thank
to
you.
our speech.